Thanks for the introduction. I would like to thank the organizers for the invitation and thank the jury for selecting our joint paper with Sergio Kleinman for the FSA award. So I'm assuming that not everybody is an expert, so I'm going to give you an introduction to start with an introduction to Einstein equation of general relativity. And I will only focus here on the Einstein equations in the vacuum. So my main object is a Lorentzian manifold, which I will very often call a space-time. The dimension is 4, so 1 for space and 3 for time. And my metric has a Lorentzian signature, and here my convention is that the signature is minus, plus, plus, plus. And the simplest example, which is not too relevant for this talk, but let me nevertheless give you the simplest example. That's the Minkowski spacetime. That would be the case where the manifold is R1 plus 3. And the Minkowski metric is given in Cartesian coordinates by minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared. Okay, so that's the framework of special relativity. Okay, so in general relativity, gravity is reinterpreted as manifests itself as the curvature of the spacetime. So I need an object to measure the curvature, and this object is the Riemann curvature tensor. Okay, for people who do not come from geometry, the curvature tensor is a 4 tensor that contains all the information on your manifold. In particular, the Minkowski spacetime corresponds to having your curvature tensor which vanishes identically, and you could think of it, if you want, as some kind of distance, as measuring a distance of your spacetime or your Lorentzian manifold to the Minkowski spacetime. Okay, and now this object here is quite complicated, so you want to take some trace of it to get a simpler object. In that case, you get, by taking a trace with respect to 2 indices, you get the Ricci tensor, which is now simply a symmetric 2 tensor. It only contains partial information on the curvature of your manifold, and with this, I can now state the Einstein equations in the vacuum, which simply corresponds to all Lorentzian manifolds with a vanishing Ricci tensor. Okay, so let me give you, so I'm going to give a more tractable form of these equations, but for now, let me already give a first property of these equations. So if I take a solution G of the Einstein vacuum equations, then you can immediately cook up another solution. In other words, if I take, yes, if G is a solution, if you happen to start with a solution of the Einstein equation, then, and you have phi a diffeomorphism, then immediately the Ricci tensor of the pullback of G by the diffeomorphism is also 0, so you get another solution. And it's so natural to go from this solution to this solution that you actually want to identify them. You want to consider that it's the same solution, and therefore you don't look at solutions, but rather classes of equivalence of solutions modulo diffeomorphism. Okay, so if you're not very familiar with pullbacks, the only thing you should understand here is that this invariance by diffeomorphism, which goes under the name general covariance, simply means that you have the freedom to pick any coordinate system you want. So that would be the mathematical way to use this freedom. And from the point of view of physics, it simply means that the law of general relativity do not depend on the choice of coordinates. Okay, so I'm immediately going to use this freedom to rewrite the Einstein equations in a different form so that you can see something, you can have a better sense of the nature of these equations. So let me first say that under this form, which is equal to 0, that would just be a second order PDE, but we have no idea on the nature of these equations. The only way to see the nature of these equations is to pick a proper coordinate system. So there are many choices, and the choice I'm going to make here is simple, although not really relevant to the result I'm going to present. It's just to give you a simple form. So the form I want to use here, the coordinates I want to use to write the Einstein equations are so-called wave coordinates, which is the analog of harmonic coordinates from Riemannian geometry. Okay, so if you pick these wave coordinates, then you can rewrite the Einstein equations, Einstein vacuum equations in the following form. You get a system of wave equations in the coefficients of the metric, and with a coupling on the right-hand side, and the coupling depends only on the metric and first-order derivatives of the metric. Okay, so if you would do this in Riemannian geometry, the operator we will get here would be a Laplace-Beltrami. Here in Lorentzian geometry, the natural covariant operator is the wave operator. And you can see that this wave operator is not the wave operator, the flat wave operator, the one in Minkowski is the wave operator in the Lorentzian metric, which is the unknown of your problem. So it's a so-called quasi-linear partial differential quasi-linear system of quasi-linear wave equations, because even the higher order terms are nonlinear. Okay, so you have in the end, because you're in dimension 4, you pick up, and the metric is symmetric, you pick up a coupled system of 10 quasi-linear wave equations. Okay, so under this form, it's pretty clear that you have to deal with a hyperbolic system of PDE, and therefore you expect that this corresponds to an evolution problem, and therefore you want to set up initial data. So let me review quickly for you how you set up initial data for this problem. So first of all, of course, because it's a wave, you expect to have to prescribe the metric and the first order, the time derivative of the metric at time 0. But let me give you the invariant formulation, the one that does not depend on choice of coordinates. Okay, so the correct invariant formulation is that you have a triplet. In this triplet, sigma naught is a three-dimensional manifold. G naught is a Riemannian metric on sigma naught, and K naught is a symmetric two tensor on sigma naught. And once you have constructed the corresponding solution of Einstein equations that emanates from this initial data, what happens is that sigma naught, you should think of it as your slice time is equal to 0, if you want. G naught, you can think of it as your metric at time 0, and K naught as first order time derivative of the metric at time 0. That would be the expansion for PDEist. And for geometers, the only thing you should understand is this is the first fundamental form, so the induced metric on sigma naught, and this corresponds to the second fundamental form of the embedding on sigma naught in your spacetime M. Okay, and it turns out it's well known that in fact not any initial data set is good enough for Einstein. They need to satisfy certain compatibility conditions known as constraint equations. This would be a geometric system of elliptic partial differential equations, but I'm not going to write it here because it's not too relevant for my talk. Okay, so what we know since what we understand since the seminal work of Yvonne Schoeberger and later Schoeberger and Garrosh is how to formulate the evolution problem of the Einstein vacuum equations. So what this Schoeberger and Schoeberger result tells you is that for any suitable initial data set, so by suitable I mean that it should be sufficiently smooth. So let me not tell you how smooth it is, it's not too relevant here. And it should satisfy these constraint equations that I did not write. Okay? So then for any suitable initial data set, there exists a unique maximal solution. And in the jargon, in the framework of general relativity, this maximal solution is called a maximal globally hyperbolic development of the Einstein vacuum equations. In fact, it's a terminology that goes back to the work of Jean Leray. Okay, so here, again, the other thing you should understand is given any initial data set, there exists a unique maximal solution. Okay, here, this is a depiction of what happens for the Schoeberger result, which is the local existence result. The Schoeberger-Garrosh is the result about the maximal existence. So, of course, the maximal solution could be very complete. The maximal development could be very complicated, but at least locally, things are fairly simple. Okay, so the main question you want to ask about this equation is what is, yeah. Yeah, so you could do it in many formulations, but you are right that the original Schoeberger result was done in wave coordinates. This is, so by now there are many other proofs. It's probably not the most efficient, but it's probably a good direct way to approach the problem. Yeah, correct. But of course, so in any, nevertheless, in any coordinate system you might want to pick, you would have to again show that indeed it's locally well posed. Thanks. Okay, so what is the general question you would like to answer? That's the question which goes under the name final state conjecture, which is a very nice, beautiful conjecture due to Penrose about the general expectation of any, or at least generic, maximal globally hyperbolic developments. Okay, but this is far out of reach. I mean, this is a large data, so-called large data conjecture. This is a conjecture about any solution to Einstein vacuum equations, at least in the asymptotically flat case. Here, let me restrict the problem to something that is more tractable, which is what happens at least in the neighborhood of explicit stationary solutions. In other words, I want to pick initial data that are close to explicit stationary solutions. So there is one that we already saw. The Minkowski spacetime is obviously the simplest solutions to the Einstein vacuum equation, and it is stationary. It does not depend on time. So, but here it's not the solution I'm interested in. The solution I'm interested in this talk are Kerr black holes, which is a two-parameter family of explicit solutions to Einstein vacuum equations, which I'm going to present in the next slide. Anyway, for now, let me ask the following question. I'd like to ask the question of stability, which means if I start close to the initial data of a Kerr black hole, do I stay close to the Kerr black hole globally? Do I stay, first of all, am I global? Don't I? Yeah, I have to prove that there are no singularities forming. Then I want to show that I'm globally close, and I want to know if I reconverge to it. So that's the question of asymptotic stability, okay? So here it's a question, let me just, a word on the motivation. It's a question of deep physical relevance because physicists believe that any dynamical black hole in the universe, and there are many of them, they will always converge to a Kerr black hole. They believe that Kerr black holes are the only possible end states to your problem. So if any black hole is supposed to converge to a Kerr black hole, the very least you can ask is that if you start close to a Kerr black hole, you converge to a Kerr black hole. And that's why it's an important question. Okay, so now let me finally present you this Kerr black hole. So here are the Kerr black holes, and for the same price, I'll give you the Schwarzschild family, which is a subfamily of Kerr black holes. Okay, so the Kerr metric, again, you could give it in any coordinate system. Let me pick a simple one, which are so-called Borionic with coordinates tr, theta, phi. And in these coordinates, the Kerr metric takes the following form, which looks a bit complicated, but fortunately, the formula itself is not relevant here. What is relevant is that, first of all, there is a formula, which means that these are indeed, as I announced, explicit solutions to the Einstein vacuum equations. Second, as I said, this is a two-parameter family. This depends on parameter A and M. A is the angular momentum per unit mass, and M is the mass, of course, of your black hole. And finally, if you look at all the metric coefficients here, even though they are complicated, they certainly only depend on coordinate r and theta, and in particular, they do not depend neither on the coordinate t nor the coordinate phi, which means that you have indeed a stationary solution. And in that case, you say that d by dt is killing. And also you are axisymmetric, so d by d phi is killing, which means that your black holes are rotating around an axis. Okay, and then if you can look at the particular case where the angular momentum is zero, in which case you recover the one-parameter family of Schwarzschild metrics, which of course were found much earlier. And the reason they were found much earlier is that they are more symmetric. They are actually spherically symmetric, and as you can see, they are algebraically simpler. The formula crunched down to a much simpler formula here, which is actually also not too relevant for the talk, except for the two remarks I'm going to make now. So I just want to explain in the next slide for non-experts what is a black hole. So let me here make two observations. The first observation is that, so here I'm going to, because it's spherically symmetric, let me forget about that part. I just want to look at the coefficients in front of dt squared and dr squared. Okay, so these coefficients, first of all, is if the coordinate r goes to infinity, then this coefficient goes to -1, this one goes to 1, and you recover the Minkowski metric written in spherical coordinates of r1 plus 3. Okay, so that means that these metrics are what is called asymptotically flat. They converge to Minkowski at special infinity. Okay, and second observation, if this metric coefficient here seems to actually is singular at r is equal to m. So in general relativity, you always want to distinguish between true singularities and coordinate singularities. This is only a coordinate singularity. I can cook up a different coordinate system in which this singularity disappears. But nevertheless, this illustrates the fact that something special happens at the hypersurface r is equal to 2m, and this is exactly connected to this notion of black holes. So for those who are not used to it, let me explain in one slide what is a black hole in the case of Schwarzschild. So again, let me recall that Schwarzschild spacetime corresponds to non-rotating black holes, while Kerr corresponds to the general case of rotating black holes. And here you have to ask for the physical restriction that the absolute value of A should be less or equal than the mass. If this restriction is not satisfied, then there is no black hole anymore, and you get a naked singularity, which is considered unphysical. Okay, so let me explain things in the case of Schwarzschild black hole. I claim it's the same in general. I apologize for experts. I will use a naive picture because I don't want to confuse people with Penrose diagram. So I will take a naive picture. I will write things in TR coordinates so that any point on this picture is in fact a round sphere. And if you would be in Kerr, it would just be a topological two sphere. In Schwarzschild, it's even a round sphere. Okay, and the way to, what I want to understand here is the so-called causal structure, which is simply means I'm going to draw light cones, okay? So if R is very large, of course, I am, as I said, I'm asymptotically flat, I'm close to Minkowski. So my light cone looks exactly like the one you're used to, the nice Minkowski light cones. But as soon as R decreases, this picture will be more and more deformed. In fact, what will happen is that this light cone will tilt more and more to the left until you reach this special hypersurface R is equal to 2m, where it is tangent to it. And in fact, if you still continue, it will tilt even more to the left. Okay, which means that starting with this hypersurface, any light cone, if you look at the generators of your light cone, they always stay inside that region. They never communicate with the outside, which means that light can never escape for this compact in space region. And that's exactly what it means to be a black hole, okay? So that's the notion of black hole. So then R strictly less than 2m in Schwarzschild is the black hole. R is equal to 2m is the boundary of it, which is usually called the event horizon. That means it's the limit of whatever you can see yourself as an outside observer, because of course we think of ourselves as being fortunately outside of the black hole. Okay, so the event horizon will be the limit of what you can see from as an outside observer. Okay, so this was the case of Schwarzschild. I claim that the picture is very similar in Kerr. And with this, let me now finally state formally the conjecture, the black hole stability conjecture, or Kerr stability conjecture, if you want. So let me remind you, you're in the context of asymptotically flat solutions to the Einstein vacuum equations, and then you have the following conjecture. And here, as you can see, this is not the conjecture. The conjecture does not concern the maximal globally hyperbolic development of Kerr. It is restricted to the so-called exterior region, which means the exterior of the black hole. In fact, the interior of the Kerr black hole is expected to be unstable. And the conjecture is as follows. So you start with small perturbations of a given initial condition of an exterior Kerr solution. And here, now I have to ask for the so-called subexternal restriction. The absolute value of the angular momentum has to be strictly less than the mass, okay? And then the expectation is that your solutions will be global, they will stay globally close to Kerr, and they will reconverge, but now they will reconverge asymptotically to a different Kerr solution with different final mass and final angular momentum. And of course, understanding this conjecture, in particular to prove this conjecture, you'll have in particular to understand what are the final states of your problem. Okay, so let me make a connection with a previous stability result. Of course, before doing that, you want to start with the simplest solution, which is the Minkowski spacetime. And the Minkowski spacetime has been proved to be stable in the monumental work of Christou and Kleinemann. Okay, so here what I will focus on this conjecture. What I want to do in the rest of the talk, I want to tell you about the history of this problem, starting with the physics literature. And then I want to present you a recent result which we have obtained on the resolution of this conjecture under the restriction that the absolute value of A is much less than M, which means the case of slowly rotating Kerr black holes. Okay, but let me start with the history. And let me start in this context. It's very natural to, the first thing you should look at is the model problem in which you simply drop the nonlinearity and just look at the linearized Einstein equations around a fixed Kerr black hole. Okay, so that is usually referred to in the literature as the linearized gravity system. Okay, so you write your metric which you expect to converge to Kerr as a Kerr metric plus a small perturbation H. So here I'm going to, for now, forget about the issue that, in fact, I expect the mass and angular momentum to change. So let me just pretend that they are fixed for now. We'll discuss the change of parameters later. And I plug this in my system. I expand my tensor. So 0 is equal to the Ricci tensor. This is Ricci of my GAN plus H, and then I just do a Taylor expansion, a stupid Taylor expansion. I have a first term, which is 0 because Kerr is a solution. Then I have a second term, which is the variation of the Ricci tensor at the Kerr metric on H. And then I have higher order term, which are at least quadratic in the perturbation. So I drop all the higher order term, and my linearized system simply becomes this simple model problem here. And what you want to do at the level of the model problem is to prove decay for solutions of your perturbation. So anyway, I'm going to make a connection to Minkowski so that you have a better idea. But what you should think of this system, you can think of this system as a coupled system. It's not really the way we look at it, but you could think of it as in wave coordinates, for instance, what you would get is a coupled system of wave equations with first order term and zero order term where the coefficients come from the Kerr geometry. Okay, so this system has been studied intensively. Yeah. For T large. So you would have some fall off. So you necessarily, this will only happen if you have initial decay in space. So you're going to look at localized data. They will have certain fall off at infinity. Let's say 1 over R square, whatever. And then you want to understand the asymptotic in time. You want to derive quantitative decay rates. Because when you move to the true, that's just the model problem. When you move to the true problem, when you couple to the nonlinearity, you will only be able to control it provided you have a very good quantitative decay rate on the linearized problem. Otherwise, you will not be able to close the problem. Okay. Okay. So this has been quite widely, studied quite intensively from the 50s to the 80s in the astrophysics literature. And started with the work of Reggie Wheeler, which was even prior to the Kerr solution. At that time, was just the stability of Schwarzschild that they were studying. And here, so there are many references. So here I stick to the references that will pop up in the talk by Reggie Wheeler, Tucholsky, Schroeder-Shekhar, and White. Okay, let me make a small detour to go back to Minkowski and tell you what happens if you look at stability of Minkowski. If you look at stability of Minkowski, now your solution is algebraically much simpler. This is the simplest solution of Einstein equation. And in that case, even though you expect here a large coupled system, think 20 by 20, 10 by 10 or 20 by 20, here it completely decouples and it just crunches to just understanding one wave equation on scalar wave equation on Minkowski. Okay, so this is due to the simplicity of the solution. In the general case, this is not at all what happens. In the general case, and in particular in the case of Kerr, the linearized gravity system is a large and entangled system, and even that model problem is non-trivial. And this is exactly what the physicists try to understand. So let me start with how the physicists approach this problem. Okay, so the physicists, in fact, I want to start with the work of Tucholsky, and what Tucholsky did was really to approach it like you would do for a standard linear system. Of course, this is a coupled system of PDEs, so there is absolutely no general theory. But if I had a linear system, my analogy would be, I want to invert a matrix, and the fact that it's coupled means my matrix is full. And of course, we know very well from standard linear algebra that the first thing you want to do to solve a linear system is to put your matrix in lower triangular form, and then you want to solve your system from top to bottom. Of course, it's a naive analogy, but I think it's still a useful one. And if you do this, if you use Gauss method, then obviously there has to be one component that completely decouples from the rest of the system. That would be the one on the top left. So that's exactly what Tucholsky tried to do. Of course, here it's a coupled system of PDEs. There is, 99.999% of the time, this is certainly going to fail. However, here, due to the structure of the Einstein equations and of the Kerr solution, it turns out that Tucholsky could find such a quantity. You could say, it's clear a miracle, algebraic miracle. He could exhibit such a quantity. In fact, he exhibited two such quantities, which I'm going to refer to as, for simplicity, just as psi plus and psi minus. These are the so-called Tucholsky scalars. And these quantities, first of all, they leave, so they are special contractions of the curvature tensor, or rather contractions of the Riemann curvature tensor with algebraically special directions called the principal null directions. These are somehow directions diagonalizing the curvature tensor. And these quantities, they satisfy non-conservative linear spin 2 wave equations. So I'm going to comment on this, but let me just say that where you're happy here is that you have a wave equation for psi plus minus with first and zero order term, and on the right-hand side, you have zero. This is where you see how you have no coupling. Usually, for any other component, you would get coupling to other components of the system. Okay, so that's why you see that it decouples. Of course, at the nonlinear level, you would see a nonlinearity here, but at the linear level, it completely decouples. Okay, so let me comment on this word. So non-conservative is something annoying, which is due to, in particular, to this first order term in red here, is the fact that these equations do not derive, the Tucholsky wave equations do not derive from a Lagrangian, unlike the Einstein equations. That's kind of annoying for the analysis, and I'll come back to this fact, but for now, let me forget about it. And spin 2 means that, in fact, you should not think as a scalar wave. This is not a scalar wave. This is a wave for tensors. In fact, psi plus and psi minus are two tensors on two-dimensional vector bundles. But anyway, let me also forget about this aspect for now. Okay, so in any case, if you forget about these difficulties, the goal is pretty clear. You want to derive quantitative decay rates for solutions to these Tucholsky wave equations, and then you want to rely on it to control the rest of your system. Remember, you have a large coupled system, let's say 10 by 10 or 20 by 20 for us, in fact. And then you want to exhibit a triangular structure very much like you would do in the case of a linear system, and to recover the components one by one and get decay for the entire system. Okay, so let me maybe comment, let me go back and even look at a simpler model problem. Let me forget about non-conservative and spin 2, about first order and zero order term. Let me just spend one slide on explaining a little bit what happens just for the scalar wave. Okay, because this is, even though the Tucholsky are more complicated, this is certainly the simplest model problem you could think of. Okay, so I want to look at scalar waves. Of course, needless to say, if I were in Minkowski, this would be a very simple problem. And let me precisely remind you, so here I want to explain what is relevant in the Kerr geometry to the problem of decay for scalar waves. So if I were in Minkowski, let me remind you that the reason why the wave equation in Minkowski decays is because the waves tend to follow null geodesics, and the null geodesics in Minkowski are simply 45-degree lines going to infinity. And that means that your waves go to infinity. So if you think of a localized solution, if I think of a localized solution in Minkowski, then the waves are going to travel to infinity, and they are going to leave any compact region, and this is how you get decay in the end. Okay, so here, in the case of a black hole, it's slightly different. There are now two ways to get decay. If you are in a black hole, so maybe let me again draw this naive picture in TR coordinates. If I draw again this picture, so this is my black hole, right? So if I have a localized solution, let's say it's here, and localized initial data, then there are two ways to get decay. Either my waves travel to infinity, or they go inside the black hole, because I know that once they reach the black hole, they never come back. So what I want is wave never coming back. So either they go to infinity, I never see them, or they go inside the black hole, they never come. These are the two ways to get decay. And of course, there is a major enemy here. Your enemy would be that there are some null geodesics that actually stay in a compact region. These are null geodesics that neither go to infinity nor inside the black hole. Okay, so that's the first observation. The first observation is that in Kerr, there are a priori obstacles to decay of linear waves, because your waves, they would tend to travel for a very long time here, and this would forbid decay to happen. Fortunately, the reason it still works is because this decay is fairly weak. It's known as hyperbolic. So hyperbolic trapping is the fact that if you look at your trap set, which is a finite codimensional hypersurface in the cotangent bundle, then this is unstable in the sense that as soon as you're off from it, immediately you go to infinity or to inside the black hole. So that's very different from what you have, what is called elliptic trapping, where there would be stable trajectories. Here, all the trajectories which are trapped are unstable. There is another annoying aspect, is the one of superradiance, or interesting according to how you want to see it, is the role of superradiance. Superradiance is the fact that, of course, Kerr is stationary, so I have a Killing vector field dt, and you know by Newton's theorem that this generates a conserved quantity, which I'm going to call energy by analogy with the energy for the wave equation, in Minkowski. So in Minkowski, the energy is a coercive quantity everywhere. In Kerr, because this vector field is timelike only for large R, it means that this quantity is only coercive for large R. near the black hole, there is a so-called region called the ergo region, for which you lose this cohesiveness. So let me draw this. Would be the super radiance would be maybe here. In fact, for large A, it will even overlap with the trapping. Well, actually, this super radiance. The way I draw it here is for Kerr. For Schwarzschild, it would just be here. But for Kerr, it's really a full. It's a full open set outside of the black hole. And then, so this was for the bad news. Then you have two good news. First one, there is a redshift region. That's a very tiny region near the black hole, for which now at least decay properties are very good from the point of view of linear waves. I mean, you get very good decay properties in this tiny region near the black hole. And of course, the other good region is a larger region, because there you are asymptotically flat, you are close to Minkowski, and therefore somehow you understand well what's happening in that region. Yeah. All right. Yeah, exactly. So exactly. So you'll have to prove that the, well, I'm going to comment to it next slide. You have to prove that there are no. So at the linearized level, this soliton, what they do is that if you linearize around your soliton, what you could have, and the danger would be to have, I don't know, eigenvalues of the wrong sign, eigenvalues embedded in the continuous spectrum, all these kinds of things that would create growing solutions. So of course, one of the things you have to do. So this, of course, this is not really. This is what you have to understand if there are not these obstructions. You also have to show that there are not what I would call obvious obstructions, which are eigenvalues of linearized operator in the wrong region of the spectrum. Yeah, correct, of the complex plane. So exactly, you'll have to exclude these modes. I'm going to say what in the next slide, but you're right. Of course, here I'm rather describing. So it happens that for the scalar wave, it's very easy to see that they do not exist, these obstructions you're mentioning. But for Tucholsky, definitely you have to exclude them, and I'm going to mention it in the next slide. Thanks. Okay, so this is what I wanted to say about the geometry. So basically, of course, the idea is to use the good news on this slide to counterbalance the bad news and to prove decay. And in fact, what you can prove, and this actually was a long story that took already 10 years even for the simplest problem, is you can prove that you indeed get quantitative decay rates, and the quantitative decay rates you get for the wave are essentially the one you think of in Minkowski, except that you don't have strong Huygens principle, but for the rest, you get the quantitative decay rate that you think you should get. Okay, so let me assume that this is done, and let me come back to the issue of decay for Tucholsky on Kerr. And let me now immediately answer your question. And this was done by Whiting. So this was maybe the closing the chapter of the physics literature on this problem. Whiting could show that Tucholsky solutions have no exponentially growing modes. So this is exactly what you were referring to. You linearize around a non-trivial state, like a soliton. So Kerr is my soliton. It's exactly the same. Kerr is my soliton. So I linearize around my Kerr soliton, and Whiting could show that there are no exponential growing modes, which means that there are no obvious counterexamples to decay. Okay, so that means the decay is not coming from the point spectrum, if you want. It can only come from the, if you have lack of decay, now you have to deal. So what I said in the previous slide is about the continuous spectrum, if you want. And this is about the point spectrum. So there is no point spectrum, so I can focus on the continuous spectrum somehow, if I would. Okay. Okay, but of course, this is, again, this part of Whiting you should understand as there are no obvious counterexamples to decay. But of course, once this is said, of course, it doesn't even tell you that there are no there could even be polynomial growth, while what you want is quantitative decay rates, and you want quantitative decay, your quantitative decay rates to be as good as the one you would get in Minkowski, for instance. Okay, so first of all, why is this Whiting result highly non-trivial? It's highly non-trivial because of this non-Lagrangian structure. If Tucholsky were deriving from Lagrangian, that would be a trivial result. I would just use the concept of energy. Well, and also, there is super radiance, but okay. But certainly you have to overcome this non-Lagrangian structure, and the breakthrough came from the work of Daframov-Sogel-Rodiansky, where they realized that actually you can use a transform due to Chandrasekhar to transform Tucholsky into Reggie Wheeler, at least in the case of Schwarzschild originally. And well, you would tell me what's the big deal? The big deal is that Reggie Wheeler itself is of course, comes from the work of Reggie Wheeler. The Reggie Wheeler equations do derive from Lagrangian. Okay, so of course here the goal is pretty clear. So because the Reggie Wheeler equation derive from Lagrangian, somehow you can export all the technology for the scalar wave, and you can prove decay for solutions to Reggie Wheeler, and then provided you can invert this Schrodinger transform, then you get decay for Tucholsky. And this is exactly what Dafemold-Sosego-Rodiansky could do in the case of Tucholsky on Schwarzschild. This was later extended by Siu and Ma, who's in the room, to the case of Kerr for small angular momentum, and independently by Dafemold-Sosego-Rodiansky. And then it was extended to the full subexponential range recently by the work of Millet and the work of Schleppenter-Kaufmann, Teixeira da Costa. And here I should mention that somehow all the works on this slide, except the one of Millet, they somehow fit in a framework that I would loosely call a physical space method, even if it's maybe, or let me call them generalized vector field methods. While the work of Millet is actually uses spectral methods, which originate from the work of Hinz and Vashi, which I will mention later. Okay, so this closes the chapter on Tucholsky, and let me now close the chapter on linear stability by spending a last slide coming back to the linearized rarity system. And here, if I come back to the linearized rarity system, now there are now you can see obstructions you were mentioning, and these obstructions, they are not growing modes, but they are in the form of a kernel. There is a huge kernel to this problem. So where does this kernel come from? It comes from the well-known fact that if you look at the stability not of a single solution, but a smooth multi-parameter solution, so here, of course, I have two obvious parameters, A and M, but of course, I have many more, because I can pull back by any diffeomorphism and still get a solution. So that's a smooth multi-parameter family of solutions. So if I take the variation with any of these parameters, I get a member of the kernel simply by the chain rule. Okay? So that means that I have here a finite dimensional kernel from variations in mass and angular momentum, but general covariance is much worse. Now, the lead derivative of the geometric with respect to any vector field is in the kernel. So that's an infinite dimensional kernel. Okay? Okay, so at the linear level, this means that you cannot quite solve the problem. The only thing you could do is solve it orthogonally to the kernel. However, at the nonlinear level, you still expect you expect stability. So where is the twist? The twist is that at the nonlinear level, this kernel is a manifestation of the fact that you will have change in the parameter of your problem. So you expect the mass, the angular momentum, and the coordinate system to change during evolution. And this is what you have to track. In particular, these parameters, they will converge to the final state. So what you need to do is, at the nonlinear level, you need to track the change of parameters and coordinates, and in particular, what are the final parameters of your problem. And this goes usually under the name of modulation theory. Okay, and here, an interesting, one of the most interesting aspects of this problem is that due to general covariance, you have to find a strategy to implement modulation in infinite dimensions for this problem, and I hope to come back to this. See how much time I have. Okay. And decay, yeah, sorry. Well, okay, and in the end, let me conclude. So the decay for the linearized rarity system was obtained in Schwarzschild by Dafemold-Sosego-Rodiansky, independently by, for small angular momentum by Anderson, Bechdel, Blue, and Siwanna, and by Hefner, Hinz, and Vashi. Again, this second work here uses the spectral methods I mentioned about from Hinz-Vashi work. And then for large A, it turns out that the work of Anderson, Bechdel, Blue, and Ma had also a large A statement which was conditional on Moravec's estimates, on energy Moravec's estimates, which were put later by the work of Schleppenter-Kaufmann and Teixeira da Costa. So with these two results together, you get large A. And there is also a recent self-contained proof with the spectral method I mentioned by Hefner, Hinz, and Vashi. Okay, so maybe let me spend one slide on nonlinear models before moving to the result. And what I call nonlinear models here, I want to talk about, I want to restrict the discussion to cases where you solve the Einstein equations, but in a simpler setting. So one of the things you could do to make your problem simpler is simply to modify your Einstein equations, and instead of looking at the Einstein equations with a zero cosmological constant, which is what I look, which is the Einstein vacuum, now you can modify them with a positive cosmological constant. And the gain, so you would tell me why you do that. Well, the gain you expect from this is that now suddenly your waves, instead of doing, so in the asymptotically flat case, waves decay inverse polynomially and at a very slow inverse polynomial rate. Here, what happens is as soon as you turn off this term here, you get exponential decay. Okay? And therefore, it makes the nonlinear problem, it simplifies drastically the nonlinear problem. So this was the approach of Hinz and Valschi. So the analog of Kerr would be the Kerr de Sitter family, and they could prove stability of Kerr de Sitter for small angular momentum in their seminal work, and this was then later reproved by my former student Alan Fong. And what they did in this work is, in particular, to prove exponential decay by exhibiting a spectral gap for the linearized operator. Okay. However, if you want to be closer to the asymptotically flat case, in other words, if you really insist of having this slow inverse polynomial rate, then another model problem you could look at is to look at nonlinear stability of Schwarzschild, in other words, the particular case of the angular momentum 0. This is not really a problem you can solve in general, because if you're close to Schwarzschild, the conjecture tells you that you will converge to Kerr in general. So if you really want to restrict the problem of just talking about nonlinear stability of Schwarzschild, then you need to restrict the class of perturbations. So there are several ways of doing it. Maybe the simplest one is to look at the symmetry class, which is preserved by the flow, and in which only Schwarzschild is member of your symmetry class, not the rest of the Kerr family. So we could find such a class with Sergi-Kleinemann, which we call polarized symmetry. It's not too important what it is. But in this class, we could prove nonlinear stability of Schwarzschild, and in particular, this was psychologically important for us because this is where we first derive our, in a simpler setting, our ideas on how to do modulation in infinite dimension, which something we call general covariant modulated spheres, which hopefully I'll have some time to talk about it. And then it was extended to a codimension 3 set of initial data by the work of Terfemos, Hotzegel, Rodyansky, and Taylor. Okay, and finally, let me mention so the result I wanted to talk about, which is our recent result on nonlinear stability of Kerr for small angular momentum. So it's actually, it consists of several papers. So there is a part which has to deal with the modulation procedure, which were, in fact, it's two joint works with Sergi-Kleinemann and then by my former student, Dawei Shen. So here, this is about this modulation in infinite dimension, in particular, this general covariant modulated spheres I was mentioning. Then you have a paper, so this is the paper that got the award. It's the paper that contains the result and the complete strategy. So it somehow it decomposes the problem in 8 different steps. And this paper contains all the decay estimates except for the Tucholsky scalars. And finally, the last paper is a joint work with Elena Georgi and Sergi-Kleinemann and contains it contains something that has to do with the non-integrable structure. So here it's non-integral in the sense of Frobenius. When you move from Schwarzschild to Kerr, there is the algebraically special frame where is now loses integrability. So we have to deal with that problem. And also this paper contains all the wave estimates. Okay, so what I want to do from now on, although I don't have that much time, I want to talk a little bit about the proof of this problem. And let me maybe start with I want to start by showing you what kind of, on what regions we actually work. So in this type of problems, you always use proofs by bootstrap. In other words, I'm going to work always on a finite space-time. And my goal is to show that whatever bounds I have, I can extend them all the way to infinity. So in other words, my bounds keep being true, so I can extend, and I get global existence and convergence to Kerr in the limit by the fact that I can push this boundary forever, okay? Which means that at any given time, I always work with the finite region. So let me explain you a little bit about this finite region. I will again take this naive picture in R and T coordinates because I don't want to use Keno's diagram here. And let me tell you a little bit what you should understand about how we construct this region. So what you should understand is everything starts with this last slice. It's called last slice, but it comes first. Last slice refers to the fact that this is the part of my spacetime which is most towards infinity, both in R and T. So it's most towards the future. That's why it's called last. But it really comes first. And what you should understand is that this is where all my choices are made. In other words, this is a hypersurface. So think a 3-dimensional manifold. which I will attach here to my spacetime, and it comes with a foliation by topological two spheres. Okay, so here each point on this picture is not a round sphere, of course, it's just a closed two surface with the topology of the sphere. Okay, so this hypersurface closed with a foliation by two spheres, and then each of these two spheres, they initialize an outgoing null cone. So for simplicity, I will keep the picture as naive as possible. So I will depict my null cones as 45-degree lines here. So they initialize outgoing null cones. I will follow them. I will have an R coordinate that cuts spheres on my cones, topological two spheres, and then I will stop at a given assigned value R is equal to R naught, which will be fixed large enough by fixed. I will stop there at this value of the coordinate R, because I know that with outgoing null cones, I can never reach the event horizon. So then I have to switch coordinate systems. And here I switch, and I switch with ingoing, like these spheres initialize now ingoing light cones. I switch, and in fact, what I will do is I will slightly enter the black hole. I will go to a value of R, where I am absolutely sure I went beyond the event horizon. So that's a bit surprising, because I said earlier that it's only the external region that is stable. It's not quite true. There is a very thin region around the event horizon, which is still stable. That's called, again, this redshift region. And I take advantage of it to completely forget about the event horizon. I don't want to track it because it's a very unstable hypersurface. So what's happening in this proof, I never see a black hole, I never see an event horizon. I don't care about it. I just have bounds and I improve them. And it's only in the limit when I converge, I come back, and given the bounds that I proved, I'm able to find that indeed I covered part of the black hole and there is an event horizon. But a priori, I don't know where it is, so it's a very convenient way to totally forget about the event horizon, which is quite unstable, and it's impossible to know a priori where it is. Yeah. No, yeah, exactly. So in other words, if I pick this assigned value of R, so let's say I'm in Schwarzschild. Schwarzschild, the black hole is R is equal to 2M. I'm going to go to R is equal to 2M minus delta, let's say. If delta is small enough, that's still in the stability region. Of course, beyond that, I could not do it. But at least if I stay very close to the event horizon, it is still in the stability region. Exactly, I will get, so naturally, what I will bootstrap is I stay close to Schwarzschild or close to Kerr. And naturally, if I stay close to Schwarzschild or close to Kerr, this value of R will ensure that I'm still in the stability region. So what I actually bootstrap is in my region, I'm able to always show closeness to Kerr and then convergence to Kerr. Okay, and that's good enough, in fact. Okay, but in any case, if you follow the construction, you can see that the only freedom I have is this last slice. And this is really where in fact, this is where modulation takes place. All my choices are done there. So hopefully I'll have the time, it's less likely, not very likely, but hopefully I'll have the time to explain you how to construct this last slice where the modulation takes place. And in fact, it starts with constructing the spheres foliating this last slice, in particular the last sphere here, which is the most important one. And these spheres are what I call these general covariant modulated spheres. Maybe let me spend one slide explaining the general strategy of the proof. I think it will be very natural in view of what I explained about the linear problem. So this is the structure that you will find in the paper that got the FSA award, although it's a very simplified, yeah, anyway, I don't think it's really useful to give you all the steps, so somehow I simplified the structure for you. So obviously, you want to start with the Tucholsky scalars. So what you will do is you want to control solutions to Tucholsky in this nonlinear setting. So there are two new things you should do compared to what I explained in the linear setting on Kerr. The first thing is that now you're not in Kerr, you're in perturbation of Kerr. So my metric in my Tucholsky wave equation is not Kerr, is a perturbation of Kerr. So that means that whatever techniques you used to prove decay for solutions to Tucholsky, now you have to make your proof much more robust to adjust to the fact that you're not exactly Kerr. And the other thing that changes is now on the right-hand side, I don't have zero, unlike in Tucholsky, I have nonlinear terms. And we know already since stability of Minkowski that you have to very carefully exploit the cancellations of this right-hand side. This goes under the name null structure. If you don't carefully exploit it, then you will not be able to close the argument because the decay that you get is too slow to make sense of general quadratic terms. It's only certain quadratic terms that you can deal with. So that goes under the name null structure. Once you have done that, and it turns out to be, in fact, the technically most challenging part of the proof, then you want to control the rest of the curvature components, the connection coefficients and the metric components. In other words, you want to recover all the components in your system, and you want to do it by exhibiting a triangular structure. And by doing so, you will have two types of equations to solve. You'll have to transport equations along the generators of the null cones, and you will have elliptic systems of Hodge type on spheres. So these spheres would be, as I said, the intersection of my cones with the coordinate R, so the level sets of all my cones. Okay, that would be a topological two spheres. And of course, you cannot do this second step in general because at the linear level, we know that there is a kernel. So you want to deal with this kernel, and in particular, to deal with this kernel, which is the modulation procedure, it turns out that there is a nice separation. The kernel due to general covariance is, you will find it in the transport equations, while the kernel due to the mass angular momentum has to do with the kernel of the elliptic systems, okay? So to deal with the transport equations, this is exactly where you will construct this last slice, and in particular the spheres folliating the last slice. So you want to construct these spheres that will track the final coordinate system. Or maybe I might have the time to say something about it. And then you want to define suitable constants M and A that will converge to the final parameter. And for the same price, you also have to track what will be the final axis. Even though you are in general perturbations of Kerr, you are converging in the limit to Kerr, which is axially symmetric. So you need to understand what will be the axis of the final Kerr you're converging to if you want to succeed in this problem. And then there is a part on top derivatives, but let me not. I want to move, so let me not mention this part on the top derivative estimate. Okay, let me maybe send. So maybe I can one more slide. Okay. Okay, so I will finish with one slide on explaining the modulation part of the proof, maybe. And the modulation part will start with this construction of spheres. Okay, so let me remind you what is modulation. Modulation is I want to track the final parameter in my evolution, which is final mass, final angular momentum, and the final coordinate system. So the final coordinate system very much depends on the gauge you chose, right? You have a huge gauge freedom, you have full diffeomorphism invariance. So here I will explain you what I do in our gauge. Of course, the explanation could be different in a different gauge. In our gauge, what is very important is I want to recover in my perturbation of Kerr the analog of the spheres of Kerr. What do I call the spheres of Kerr? In the TR, remember there was this TR theta phi coordinate system. In the TR theta phi coordinate system I presented, I want to recover the spheres of constant T and constant R. That would give you topological two spheres. That would give you, in short, that would be round spheres centered at origin and at time t. But here, these are in general topological two spheres, and these are two parameters, right? You have two. These are a two-parameter family of spheres. So this is the spheres of Kerr that I want to track in my perturbations of Kerr. And of course, what is very important is that I should be able to find preferred spheres in my space-time, which I consider as the best approximation to these spheres. So it's a best approximation problem. And for that, I need to find exactly the right number. If I have two little spheres, if I don't find a two-parameter family, I will not be able to construct my last slice. If I find too many, my risk is that I will pick the wrong coordinate system. So this is exactly what we did in the two-joint proof of Sedgwick-Kleinman. We could design a procedure to construct a unique two-parameter family of preferred codimension two surfaces in general perturbations of Kerr. In other words, here the very important aspect is that you construct exactly as many spheres as you need. Okay, so there is an analogous problem in the seminal work of Huisken and Yao, where they construct a one-parameter family of spheres in a three-dimensional Riemannian manifold. But here it's actually very important that you should construct a unique two-parameter family of spheres in a four-dimensional Lorentzian manifold. And okay, so maybe just a word. This relies on fixing well-chosen geometric quantities to agree with their Kerr value. The geometric quantities would be, for those who are familiar, the two null expansions or the two null mean curvatures, and a third quantity called mass aspect. And of course, the definition is quite natural. The difficulty is to show existence and more importantly, uniqueness, that you construct exactly the correct number of spheres. And finally, so this settles really the modulation due to general covariance. In other words, these spheres that we call general covariant modulated are the ones that will foliate the last slice. And then you need to, so this settles the issue of the coordinate system. Then you need to settle the issue of the mass angular momentum. And what you will do now is, the nice thing about it is, it's important to start with the spheres. And once you have them, you're left with finding an invariant definition of mass angular momentum on such special GCM spheres. So for the mass, it's quite easy because there's known to be a very good notion of mass in the literature called the Hawking mass, which does the job here for us. For angular momentum, actually, that was more tricky. There are many definitions in the literature. And it turns out that none of them was really working for us. So we came with yet another definition. And for the same price, the way we define the angular momentum allows you to track the axis of symmetry of the final Kerr. So it allows you to track to which axis will converge in the limit for the same price as part of the procedure. And then what we use for it, I mean, the way we find an intrinsic definition is by relying on the uniformization theorem. Okay, stop here. Thank you very much.
Very exciting talk. Any question for Professor Szeftel?
So of course the fact, so usually to be in a perturbative setting always help, but so the fact that you are considering slowly rotating black holes, where does it enter in this proof? So can you?
So it enters only one place, in fact. It enters, sorry, that's not the correct way. Well, in fact, okay, last slide, maybe I can show, but okay, it enters only in this last paper, which is joint with Elena Georgi and Sergio Kleneman, and in fact, it enters only in, so this is the paper that contains the wave estimates. In other words, all the papers in the sequel, they work for large A without any problem, but this paper uses the smallness of A, and it always uses it in a special part. It uses it when you derive certain estimates for the wave equation or Tucholsky equations. And for these estimates, we use the smallness of A because maybe, so the point is that for large A, the trap set and superradiance, they start overlapping. And now you have two difficulties that overlap that makes it so small A, what it allows you is to separate these issues. So it's really just for the estimates for the wave, and the important thing is that for small A, there's really something simpler. Yeah, there's a separation of your enemies, if you want, which makes the enemy. So what you will have to do for large A is really to extend the wave estimates that are done here. So this is what I have done for the scalar wave with Siu and Ma last year, but we still need to work on Tucholsky, and then there are other, but basically it's really about estimates for the wave and Tucholsky. So the time decay that you get is in fact, it's in the far region is consistent with Minkowski. So it's the same as stability in Minkowski. In the near region, in other words, close to the black hole, and in interior region, in the interior of the black hole, it's really weaker, but it's time integrable, so it's good enough. In other words, in the interior, you would expect more, but you have at least 1 over T1 plus delta that allows you to close the argument. So I don't think it's optimal. But sometimes in these problems, you want to close with the least decay and not the most. So.
We have one last question. So
you mentioned the method, the spectral method by Darji and collaborators.
Exactly.
How different is this method from yours, and how different are the results obtained?
Okay, very good question. So maybe let me go back to the. Yeah, I should go back to so it was introduced in this result, but maybe let me rather go back to the Hefner-Hinz-Vergier result here, because this one is the asymptotically flat case. It's a completely different method, right? So the first thing you do in this method is you take the Fourier transform in time, and and now your time becomes your spectral parameter, and you just want to talk about invertibility of the corresponding elliptic operator. So it's a very efficient method because somehow it immediately it allows you to prove decay It allows to have a statement where you can say, even what does no decay can tell you a decomposition. I have a finite number of possibly growing modes plus a decaying part. This is the strength of this method in particular, is that it absolutely does not care about the Lagrangian structure of the equation. I do care. I mean, the methods that we use, that I explained, they fundamentally rely on the Lagrangian. The Hinz-Faché method does not care at all about the Lagrangian structure. They can do it even without. So that would be. In terms of results, well, in terms of results at the linear level, I would say they are fairly comparable, but so far they could not, at least they could extend it in the Kerr de Sitter case, but in the Kerr case so far they have no proof of nonlinear stability, but you know, I wouldn't exclude that. I'm not sure. I wouldn't exclude that this is doable, and if doable, then I would expect similar results here.
Sorry, we are wrong on time. So if you have a question, please talk with Jeremy in the public region. Thanks, Jeremy, again.